All right. So this is how you fit a bunch of papers into one PCC talk. This is actually 4 papers in one talk. I'm going to be talking about the lunar crater chronology, how it's been 60 plus years, and we have no idea how old stuff is on the moon yet. I'm going to be talking about researcher variability, revisiting a 2014 and 2025 study in a new paper that is still under review because very few people can actually review it who are not already authors. I'm also going to be talking about examining lunar AI-based crater databases. This is a published paper that came out a few weeks ago. And I'm going to be talking about doing crater statistics. So, with my skepticism of AI, I did have ChatGPT generate some of my title slides. The purpose of this one is a lunar crater chronology, showing how you have a bunch of people using different tools to examine lunar craters. And that's a hint as to why we still don't have a lunar crater chronology that we all agree on. So the foundational concept between the chronology really rests on 2 things. One is that craters are statistically independent events, spatially and temporally, and that on average, more craters are going to be an older surface. The idea is that we can measure the crater spatial density. This is craters larger than 1 kilometer on a given surface that has a sample from either Apollo, Luna, or the Chang'e missions. We can do that a lot, and then we can fit a function to it. And then what you can do is you can take that function, go somewhere else, measure crater spatial density, and get out an age. Easy peasy. That is the left side of this figure. The right side is showing you that there's a bunch of indirect things also part of the chronology that I don't have time to get into. But it is easy in theory. However, it is not easy in practice. This plot, which did not show up well on the projector, shows that there are 8 existing lunar crater chronologies. Over most of lunar history, and let's see if my mouse shows, it does not. Over most of lunar history, we agree within about a factor of 2 to 3. And Bill Hartman, who pioneered some of this work, has always maintained that the chronology is accurate to about a factor of 2 or 3. The problem is when people don't actually carry that through in their analysis, which I think they should. The reason that we disagree is that we can disagree on just small little points. And I can't show my mouse. Oh well. If you go down to the bottom left plot and you look at one of those, I'm going to present from back here. Oh wait, that's just the room. Yeah. All right. If you go down to that bottom left plot and you see a upside down triangle that is close to the legend, that is one of Stephanie Werner's points for her chronology. If you were to shift that crater spatial density by a factor of 2, which is not unreasonable in terms of the uncertainty, it would completely change the exponential part of this function. So we have a very undersampled function that's supposed to cover 4+ billion years of lunar history. Another reason why we disagree is shown in this very complicated figure that I'm going to go through very quickly. The top is showing you 3 different data sets, and it's showing you people mapping differently for the Apollo 15 lunar sample. So the little arrow that is very hard to see in the slide, but there is an arrow pointing to a small white dot. That's where the Apollo guys landed, and that's where they sampled. This is the Hadley Real area. And what you're seeing in 4 different colors is you're seeing how different people have made their mapping for crater counts to tie this lunar crater chronology together. We all disagree on our mapping. If you get out to the middle plot, we also disagree on our crater spatial densities for these areas. This is a case where some people are relatively low, some people are relatively high. But it's not just that we disagree on the crater spatial densities, we disagree on how to assign error bars. So the yellow line that is at the top of that middle plot is Iqbal et al. And their work is based on 15 craters. And you can see the size of that error bar. If you go down to the middle cluster, that's my work, that's 330 craters, a factor of 20 more. And yet I have the same size error bars. Now, just square root of n statistics, you would think that her error bar should probably be 5 times larger than mine. This is because we don't just disagree on how you assign crater spatial densities or our mapping, but we also disagree on how to even quantify the error. And so the reason why we have different chronologies and we don't agree yet is because we have different mapping, different agreement on what a crater is, treatment of secondaries, whether we subtract the area occupied by secondaries. We don't really agree yet on how to tell if a crater is superposed on the surface or not, because you don't want stuff that's buried beneath the surface. We disagree on how to decide what's saturated, on whether topographic diffusion should factor in, how to assign a minimum diameter to our completeness counts. We disagree on the treatment of strength, because different materials will form craters differently, and yet only one study that has done this actually factors in terrain strength. When you extrapolate N1, because you don't always measure 1 kilometer craters, if you use a different production function, you get a range of N1 that differs by more than a factor of 3. How do you factor that in? How do you propagate all of these uncertainties? And the answer is, don't really know, but it's even more complicated than that, because we have a question of, let's say I make the most rigorous crater chronology ever. Nobody's actually going to use it the right way, because we are never actually going to go in and use max scale images, sub-meter per pixel images, and decide whether every single crater is actually superposed on the surface or not by looking for lava embayment on the rim. Nobody's going to do that. And so we have this question of what happens when the tool and the application diverge. And this is an open question, and I don't know the answer to it because, as I said, you could be super rigorous in how you create a lunar crater chronology, but then nobody's actually going to use that tool the same way that you created it. Another question is this whole issue with the production function. The Neumann production function was used in concert with creating the Neumann chronology. That means that it has built-in assumptions, and if you use a different production function, you cannot use the Neumann chronology. They are incompatible, yet people mix and match all the time. So we have this correlated system that I don't think a lot of people quite grasp just how correlated it is. And we need to ask some of those questions of, is the Neumann production function accurate? And some people would say, no, it's not. And we might need to revisit some of these fundamental assumptions. Another question is about how do we do this error propagation? How do you quantify an uncertainty in the mapped area? I don't think this is something that we've ever really thought about. I don't see Jim or really hardcore mappers in the room, but maybe something to think about later. So these are open questions. This was a review paper. Hopefully see it out in a couple months in Annual Reviews of Earth and Planetary Science, which takes me to the next paper in this talk. And this is Crater Repeatability Revisited. The image for this is sort of showing the archetypal gods and goddesses of why we disagree in our crater counts. We have bias, we have scatter, we have different preservation states, completeness issues, machine vision, and that introduces an entirely new set of complications. So in 2014, we published what I might refer to as a now seminal study of crater variability, where we had only 8 people, but we were able to do a lot with 8 crater experts and show that we disagree a lot more than we think we didn't disagree. This was a case where we showed that just in crater number, we disagree by up to about 45% in the highlands. In the Maria, it's closer to 15 to 30%, depending. In 2025, in a talk that I presented here at PCC in 2024, we took 3 of our experts and we looked at the same terrain under different lighting and camera geometries, along axes of incidence angle, mission angle, and phase angle, and we looked at how much we vary in the same image, even the same person, how much they vary in the same location just based on these illumination and geometries. And I'm going to thank all the reviewers who reviewed these papers. Of course, that's a lot of time and a lot of Stuart droning on giving this talk. So what we did for this new study, what our study is besides still in review, is that we started with the professional crater data from 2014 and 2025. We recurated it, added preservation state, and used a new cluster code that I developed, and we analyzed it in a lot of different ways, focusing on a Bayesian driver, with a question instead of how much do we vary from a consensus, it's how much do we vary from each other, which is a different question and is more along the lines of what we actually do in everyday life. So I'm going to show you through a lot of different graphs. You don't have to read them all. You don't have to understand them all. I'm going to summarize them for you. The top row is showing you diameter bias. And this assumes that our cohort averages together to zero bias. If you don't assume that zero as the mean, you have a degeneracy and you can't solve this problem. If we assume a zero as the mean, then we can look at this and say, how do we vary in these different terrains? And some people vary really, really steadily. It's highly repeatable. So the person who was the light blue, consistently in different terrains and across a decade of time, were consistently about 7 to 8% smaller in their crater measurements than the average. Other people varied also very consistently on NAC images, but not WAC images. So the black point was too large by about 8% on the two NAC images, but on the WAC, they were closer to the average. What this shows is that sometimes we're consistent in our variation, sometimes we're not. And we can also look at scatter. So if you think of a dartboard, the bias is how far away you are from the bullseye, and the scatter is if you throw about 100 darts, where do they land around that bias point? So the scatter, we have a floor of about 5%. That is the best anyone could do in this cohort. That was Clark Chapman. I'll give him props. He's been doing this for decades, so I'm not surprised. And everyone else was larger than that, up to 10%. And what we can do is we can graph each of these along different axes, and we can make the plots at the bottom. Those are even scales, 5% tick marks. And those ellipses are where humans lie, at least within our cohort. So that means that if someone is beyond that, say in AI, they do not do as well as humans do in terms of bias and scatter. Another thing is that when we resolve these plots in diameter space, which I'm not showing you because those are really complex plots, when we resolve them into diameter space, our minimum bias is at about 15 pixels. In the 2014 study, we said that if you go smaller than 8 to 10 pixels, you are no longer repeatable as much with the ensemble. We're raising that floor. We're saying 15 pixels is now where the minimum bias and scatter are. Anything smaller than that, and you start to get into repeatability problems. And if you're smaller than 10 pixels, you're really getting into repeatability problems. So this is a sad result, but it is a result nonetheless from this work. I'm going to very briefly say that we also look at the power law slopes, and you need 4 people to measure craters independently before you can rely on your slope. And that's just how numbers work. If you're just you have no idea how good you are. If you have 2 people, you still don't know how good you are. We needed about 4 before we settled on something. The other part of this is that least squares fits are really, really bad. That is the pink lines, those cluster way far away from all of the other points, and I'm going to address least squares fits again later. Like this slide right here, because we also looked at ages. The column on the left is ages from each of these surfaces from each person, and that is using traditional methods. The middle plot and the top plot actually have the radiometric age of those samples. And so we can see how well do we reproduce the actual radiometric age from these craters. And the answer is not really well using traditional methods. Only 2 people encompass that with their error bars for the NAC region, and only 2 or 3 people encompass it with the WAC region. That means that either we're not getting the right answer despite having 8 experts doing crater counts, or maybe we should be using different methods besides traditional ones for assigning ages, which gets into a Bayesian approach, which is a teaser for the 4th part of this talk in the middle and right columns. The take-home point of that is that they do encompass that radiometric age, and in many cases, the mean shifts closer to it. That is a teaser for later. In the interest of time, moving to the 3rd part. Okay, how good is AI for craters? In this case, the image here that looks really complicated, because it is, if you look at any crater database with, any region of the moon with 8 crater catalogs overlaid, it's really complicated. And so what this is showing is a bunch of machines on the outside trying to map craters going all over the place. And then you have a guy sort of in the middle with his head on his hand, it's probably me, looking at the moon and saying, no, this is where they're supposed to be. So the motivating idea behind this was that Stuart, as in me, has reviewed a lot of AI, mostly machine learning based creator detection papers in the last decade. I'm asked a lot because people usually use my databases for their training or their ground truth. And I will just say eyebrows have been raised about quoted metrics, especially when they just look bad. This was quantified for Mars by Lee in 2023. I think that's the fastest review I ever turned around in 2 hours after being asked to review a paper. They compared 3 AI-based creator databases on Mars, and they found that when they applied uniform metrics and required that the creator location and size be within 25% of what a human would do, that the quoted metrics in these papers dropped like flies. They dropped, in his case, by a factor of 2 to 3. Things like from 0.7 to 0.3 or 0.25. So I said, well, there are a lot more lunar crater AI-based databases now. How do those do? And not just with 25%, but let's say, how do they do compared to human variability? So those ellipses that I showed you before in terms of bias and scatter. Let's constrain things to what humans do in terms of getting location accurate to within 5% and diameter accurate to within about 10%. And you can see based on the images in the bottom right of this slide, those are actual published AI-based creator databases. You might get an idea for where this talk or this section of this talk is going. Not to bury the lead, they don't do well. Most were about 10 times worse than their self-reported metrics when constrained to a human variability tolerance, which is, I think, significant. Your mileage may vary. More complicated plots, I'm going to explain these quickly. The horizontal lines are metrics that were quoted in the papers. The left 2 plots are precision. The right 2 plots are recall. Precision is of what's found, what's actually real. Recall is of what's real, how much was found. So these are 2 very different things, but they're both critical metrics. If you ever review an AI-based grader paper and they do not report these metrics, reject it. That is Stuart's advice today. They are critical machine learning-based metrics, and what they do is that they show you how well these things actually do. And I recalculated all of these metrics based on that strict matching tolerance. And I also resolved it in diameter space. So most of these papers say our precision was 0.7, our recall was 0.6, period. You actually need to resolve it in diameter space because precision and recall vary with diameter. And you can see that on these plots. Especially with recall, there is a good peak in most of these data sets around 50 to 100 kilometers. They found most stuff. When you go down to 1 kilometer or 5 kilometers, they did not find most stuff. And most craters are small. And because of these recalculated metrics, because they didn't find a lot of small stuff, that's why their metrics dropped when I recalculated them by a lot. Bias and scatter, I told you I'd get back to these. So I have replotted the data from the 2026 paper that's in review. Those are the nice, pretty colors. I've replotted those ellipses. And then the AI-based crater databases for the moon are the bigger diamond-ish things. Most of them are really high up on the plot. 3 of them are really close to where the humans are, but still outside of those ellipses. However, it bears mentioning what those actually are. So S12 is Salamunikar et al. 2012. They were not a machine learning database. They were a deterministic AI algorithm, and they checked every single feature that went into their catalog. So the AI found something, they said yes or no, and then it went in or not. S19 is not Silber, but Silbert et al. 2019. Some of you may remember the press releases of AI discovers 6,000 craters on the moon. No, they just used a database that was incomplete for their training. But most of those craters were on the Maria. So they only looked at 28% of the moon. Most of it was Maria, where it was easy And so their metrics are going to be better because they looked at an easy area. Then there's W21, that's plots really close. This is weighing at all 2021. This is one that if you get me drunk, and I don't drink, so good luck. I will give you a lot about this particular paper because they basically took my crater database, added Gaussian noise, and published it, and said that their AI found it. And it's kind of like, yeah, you're going to do pretty well if you look at the back of the book before the test, or during the test. So, again, I have more on that I'm not going to mention. Paper 4, re-examining crater statistics. So in this beautiful image, we have in the dark and stormy gray mountain, traditional methods, cumulative histograms, least squares fitting, frequentist stuff. In the bright, sunny, beautiful, colorful valley, we have new methods, new statistics, Bayesian approaches, and coming out of the lake like Excalibur, we have a new method of plotting data, a new method of fitting slopes, and a new method of assigning ages. So let's talk about how we get pretty. This paper by Sam Bell, and me, Stuart Robbins, addresses 3 critical areas: ages, slopes, and displays. And Sam knows his math really well. I don't, so I might not be able to fully answer questions about this one. But I can talk about it as an overview. The age problem. Frequentist methods are faulty. I've said that now a couple times. That's because they assume things that we don't always, or that aren't always real. We also can't easily propagate uncertainties nearly as well in a frequentist approach. And Michael et al. In 2016, after a 2015 workshop, actually introduced this mu notation. So if you've ever seen age with the Greek letter mu in front of it, that came out of the 2015 workshop and is credited to Michael et al. And that mu is supposed to be, quote, a perpetual reminder of all of these unaccounted for uncertainties. However, I say we, Sam developed a method that can propagate these. The basic idea is that instead of treating every crater that you measure as a discrete thing that you plot up and then align curves to, you treat the population as a probability distribution. Once you've treated it as a probability distribution, you can say take an error model of, say, how much people scatter or bias in their crater measurements, and you can multiply that in to your population. You can take another error model of the chronology uncertainty and multiply that in. You can take another error model of even where you estimate the minimum crater diameter and multiply that in. And by doing that, you now have this age distribution that has been widened and shifted based on these uncertainties. I'm going to show you, not explain, but show you what it can do. This is Canala crater on Mars. It is a very young crater. I measured craters on its ejected deposit in CTX and HiRISE. Those ages should be the same because it's the same ejected deposit. They're not. So if you look at this very complicated figure, Sam, I pointed out in the top middle, those are the ages that you get with the CTX counts and the HiRISE counts. And I put the ages over to the side. Those are not the same, not even close to within 1 sigma. What we can then do is once you convolve in all of these different error kernels, you get an age distribution that suddenly now agrees, with the bottom right showing you the new CTX-based age and the new HiRISE-based age for this ejected deposit. Now, not only are those closer, but you will note that the error bars are larger, perhaps uncomfortably larger. I looked at those error bars and thought, Sam, nobody's going to use this because your error bars are bigger. The reason that error bars are bigger is because we are now actually factoring in all of these errors that we weren't before. Error bars before were only based on square root of n counting uncertainty, not anything else. So what we've done is we have now added in all of these extra uncertainties, which means by definition, your error bars have to get larger. So while I am uncomfortable emotionally with these large error bars, it's what it is. This is the reality of the state of crater-based stuff. And I think it's something that we need to accept, use, and move on. Can I interject real quickly? Yes.
Sorry, sir. Going back to that,
hide this closely.
going back to that comment about Bill Hartman's work, though, the disclaimer for lunar chronology was always a factor of 2 to 3, and that's less than a factor of 2 to 3. So
There is a chronology kernel uncertainty factored in here.
okay.
But yes, so there's a yes, 2 to 3, but that should shift both ages, not make them agree with each other. So it's not a factor of 2 to 3 brings them together, it'll shift them.
Got it.
All right. Next is the slope problem. This is one slide. Never use least squares fitting. I think I've now said this 4 times. Least squares fitting is just wrong. The 2018 work that we did for recommended maximum likelihood, it's also slightly biased at small numbers. Sam developed a better method that has almost no bias whatsoever. I am not going to show you math and pictures of lines getting slightly closer to data. So, oh, I lied. That was an Easter egg for myself. I hit it on this computer, but didn't copy that version over. Right. So then we have the display problem. The problem with the display problem is that the way that we look at our data should not change how we interpret it. If the way we look at our data biases how we interpret our data, then we're displaying it wrong. And this is something that Clark Chapman has been harping about since 1967. There is a Chapman and Hefner paper that I keep citing because people still keep ignoring it, where he pointed out a lot of the problems with the bin methods. Things like, where do you put that bin center in a power law variable distribution? Things like square root of n error bars. They differ depending on how you bin things. Cumulative error bars are different for a given diameter than incremental, which is different from differential, etc., etc. The Robbins et al. 2018 also has its problems. I will admit that. It is wiggly woggly, and a lot of people did not like that. I still don't necessarily like it, but my emotional state should have nothing to do with my research. But sometimes it does. There are also artifacts at the minimum and maximum diameters, just because of how it is constructed. So we, and by we, I again mean Sam, developed a method that removes a lot of this bias and better reconstructs the source distribution. It is called SASH, which stands for Slanted Averaged Shifted Histogram. All we've done is actually added slanted. The average shifted histogram is in use in other fields of science. How does this work? You make a histogram. I know, I just said histograms are bad. You make a histogram, but instead of a step function, you slant the top of that bin. You start by slanting it with a known power law such as -3. You then shift the start point a little bit, and you make your histogram again. And then you shift it again, and you make it again, and you average these together. Then you go back to the very beginning, and you make your histogram, but this time instead of a slant with a -3 slope, you make it based on the previous iteration's slope at that point. And you iterate this a couple times. This is showing that diagrammatically, people who are actually on the Zoom can see this a lot better than people in the room. But the upper left is showing you a shift, not a shifted, it is just a slanted histogram. Panel B is showing you what happens when you put 2 together. Panel C is showing you what happens when you put a lot together. And D is when you put a really lot together. And then E is where you repeat the process, but you use the local slope from panel D. So what we've done is we've shown that this will reconstruct the source population better than other methods. And I'm actually going to just exit and zoom in like that. So the source population is the Neumann production function shown in this black curve here. Nice and neat. The classic binned methods are shown in the binned points, obviously. The green is the wiggly woggly Robbins et al. 2018. The error envelope, I think, centers nicely on the original population distribution. And then the blue curve is SASH. So it has reconstructed that really, really well, all things considered. Okay, I know I'm at my time. Summary, I'm going to go into the break by 45 seconds. Martin, look like you're gonna kill me. It's just my face. The creator chronology take-home question is, should the tool reflect perfect rigor, or should it reflect the rigor of its users? I don't know the answer to that. My OCD says one thing, my practicality says something else. On the researcher variability, I've been saying this for a decade. I'm just gonna send out an email next week to everyone and say, all right, here are the images. Anyone who can volunteer to count them, let's do them. Because I think that it needs to be redone with more people. Lunar AI-based creator databases, I have a no robots thing right there, but really the take-home message on that is check whatever you're going to use first, even if it's from me. Make sure that it's actually appropriately precise and accurate for what you want to do. And then for the bottom point, giving you time to take a screenshot or type it down, the code is out there for the age problem, the slope problem, and SASH. This is on GitHub. It's all in Python. It is pretty easy to install and use if you know a little bit of Python. There are example workbooks. It's great. So thank you for giving me an extra several seconds. I'll leave my summary slide up for however long. Yes, thank you.
Looks like we're heading into the break now for a photo. But first, I'd like to present Stuart, the first of its kind, longest title PCC 2026 conference ribbon.
For me?
For you. You can impress your friends at parties with that.
Ask my friends first.
All right, very great. I see, Dave, that you have a question online.
It's weird because I don't see it.
His hand goes up.
Hi.
Oh.
Great talk. Can you all hear me?
Yep.
Yeah, great talk, Stuart. I actually want to ask a question that would, since you combined all these projects into one talk, I'm going to ask a question that unifies a couple of them, if I can. It has to do with the chronology and the error propagation. So one of the major underlying assumptions I think is underappreciated about the Neuquén production function, actually most production functions, is that they always make the assumption that the size frequency distribution doesn't change through time, so that those are independent. I think that's particularly as you go back early in solar system history, there's I think a lot of reasons why that's not the case. So if we were to think about how to capture the chronology uncertainty somehow in your final method, how might you want to go about doing that?
Very carefully. I think that you would have to add in a time variable component to the solution, which could probably be done. And then that would just get involved in, because you don't know that you're almost going to have to do an iterative method of solving. Because if you don't quite know when stuff formed, then you're going to use one production function. And if you shift when it formed, then you're going to have to use a different one, which would give you a different age. So it's almost an iterative thing. It's an interesting problem that I don't necessarily want to think about right now. But
All right,